The modern Sahara Desert covers 3.6 million square miles of northern Africa. It is a massive, hyper-arid expanse of shifting sand and exposed bedrock, where surface temperatures can exceed 120 degrees Fahrenheit. Yet geological records confirm that between 11,000 and 5,000 years ago, this exact landscape was a vibrant green ecosystem. Extensive river networks, deep lakes, and sweeping grasslands supported a dense population of early humans and diverse wildlife. Finding physical proof of that lush past is notoriously difficult. The wind continuously reshapes the dunes, burying ancient settlements and geological markers under dozens of feet of abrasive sediment. Traditional surface excavation cannot penetrate that sheer volume of moving sand. To locate the physical remains of the Green Sahara, researchers have to rely on remote sensing technology, capable of looking completely through the upper crust of the Earth. The initial evidence for a hidden, intact ecosystem came from orbit. Satellites equipped with synthetic aperture radar, a type of sensor that uses microwave pulses to map surface topology, detected a massive structural anomaly deep beneath the eastern desert. Because extremely dry sand lacks the moisture to absorb microwave frequencies, these orbital radar pulses pass straight through the dunes. They only bounce back to the satellite when they strike denser, solid geological structures buried far below. When researchers compiled those reflection points, the radar data mapped out the clear ghosts of ancient paleochannels. Paleochannels are the inactive, buried remnants of ancient river systems. The data also indicated massive empty subterranean voids connected to these dried waterways. With precise coordinates generated by the satellite, researchers no longer had to guess where to dig. They could mount a targeted physical expedition directly to the anomaly. Reaching those exact coordinates requires navigating a convoy of heavy equipment and specialized personnel hundreds of miles away from paved roads or established supply lines. Operating in this remote environment means the team must bring their own infrastructure. They rely on portable, solar-powered data centers to process terrain data in real time, functioning completely off the grid. The orbital satellite provided the macro-level location, but those wide-angle scans lack the resolution needed to sink a drill shaft. The team has to verify the exact boundaries of the subterranean voids from the ground. Navigating the dunes only gets the equipment into position. The critical phase of the expedition requires pointing their instruments straight down into the bedrock. To find the exact drilling point, the team uses ground-penetrating radar, or GPR. GPR is a geophysical method that uses radar pulses to image the subsurface, allowing researchers to detect buried objects and changes in material without digging. The mobile GPR unit emits high-frequency radio waves directly into the sediment beneath the cart. The system records exactly how long it takes for waves to hit a buried cavity and reflect back. Algorithms translate these return times into depth measurements, generating a three-dimensional map of the cavern structures beneath them. This high-fidelity subsurface map proves the voids are actually there, providing the exact coordinates and depth required to begin a heavily resourced physical breach. Drilling through packed sediment and solid bedrock is a slow, mechanical process. The team carefully extracts core samples until the drill bit finally punches through the crust and enters the open subterranean pocket mapped by the radar. Inside these sealed caverns, researchers uncover the perfectly intact remains of prehistoric megafauna. Megafauna refers to the large, extinct animals that once roamed the earth, like massive early crocodiles and ancient river hippos. The heavy layers of desert sand above acted as a geologic hermetic seal. By blocking out oxygen, moisture, and scavengers, the environment prevented these organic remains from decomposing over the last several millennia. By breaching the surface crust, the team has opened a pristine geological time capsule, revealing direct physical evidence of the Sahara's biological past. This subterranean space preserves a high-fidelity record of both the local biology and the broader climate history of the region. This chart shows the decline in regional rainfall over thousands of years, constructed from chemical data extracted from the ancient water trapped in these deep aquifers. It illustrates a rapid transition from heavy precipitation to severe drought. By cross-referencing the isotope levels in the water with the radiocarbon dating of the megafauna fossils, Scientists can reconstruct the exact timeline of when the Green Sahara rapidly collapsed into a desert. Tracing the mechanics of that ancient collapse provides modern climatologists with crucial baseline data. Understanding exactly how quickly a rich ecosystem can permanently dry out helps researchers build more accurate predictive models for current global climate shifts. The survival of vulnerable agricultural regions today depends directly on our ability to read these ancient environmental warnings trapped inside the Earth. Discoveries like this prove that the surface map of the Earth is highly incomplete. Massive, intact geographical features remain completely hidden from plain sight. We do not need to look off-world to find uncharted territory, the next major frontiers of physical exploration.